All right, let's talk about the mole map for just a little bit. Notice we can go to mass of one chemical species to moles. When we divide by molar mass, Avogadro's number gets us to number of particles. We can even go to volumes of gases. We're not going to worry about that right now. But here, when I go from moles of one item to another, you can label this mole ratio. And the mole ratio will come from two different spots, never two different spots at the same time, but it'll come from the subscripts in a formula. Let me just come up with the favorite reaction, burning hydrogen, not balanced. So I can say there's 2 atoms of hydrogen for every 1 atom of oxygen, or I can say 2 moles of hydrogen for every 1 mole of oxygen. So the mole ratio can come from the subscripts in a formula, or I can say for every 2 moles of hydrogen gas, I need 1 mole of O2 gas. So this mole ratio can come from coefficients in the balanced chemical equation or from subscripts. And hopefully we'll do some examples that will illustrate that today. It's been so long, where'd we leave off? We'll just start here, I guess. The mole, it's like the word dozen. It can change depending on whatever we're talking about. For elements, the molar mass is the mass of 1 mole of atoms of that element. For compounds, the molar mass is the mass of 1 mole of molecules or formula units of that compound. And that's how we're going to convert from mass to moles. So you've already had some practice doing this, like on a quiz. What is the formula mass of carbon dioxide? You take the mass of 1 carbon, sum it with the mass of 2 oxygens, and you get this 44.01 atomic mass units. And that would be the mass of 1 molecule. If I go from molecules to moles, I use this unit grams per mole. That means 44.01 grams of CO2 is the same thing as 1 mole of CO2. And that also means I have 6.022 times 10 to the 23rd CO2 molecules. Converting between grams and moles of a compound, calculate the mass in grams of 1.75 moles of water. So we have to go 2 times 1.01 summed with 16, and we'll get 18.02. And so that is the mass of 1 mole of water. 1 mole of water equals this. So here is that unit factor. And we can use it to multiply 1.75 moles H2O and get moles of H2O to go away. And we're left with 31.5 grams of H2O. So on the mole map, oh lovely, we went from moles of H2O multiplied by molar mass and got to mass. Any questions? Now if I know the number of particles, I'm going to divide by Avogadro's number, and that will get me to moles of NO2. And so here is the molar mass, where I take 14.01 and sum that with 2 times 16 to get to 4601 and multiply that across. And so I've gone from particles to moles to mass. And you'll see these unit factors on the mole map. So once again, this gives us ratios. 2 oxygen atoms to 1 CO2 molecule. 2 dozen oxygen atoms to 1 dozen CO2 molecules. All right, so now we're going to use that middle part where we have a mole ratio. Here it says find the number of moles in 1.7 moles of calcium carbonate, CaCO3. Find the moles of O. So when we look here, we see 3. So we can say 3 moles of oxygen for every 1 mole of these things. 1.7 moles of calcium carbonate For every 1 mole of calcium carbonate, I get 3 moles of oxygen. And now that comes out to be 5.1 moles of oxygen. All right, how many grams of sodium are there in 15 grams of sodium chloride? So at the beginning, very beginning of this chapter, I want to get some closure on that. It said, according to the FDA, I think it was 2.4 grams of sodium. And we asked, how much sodium chloride can we eat? And we're going to answer that today. 2 different ways. Got off to a weak start. Sorry about not starting on time. Should check, Moodle should have updated your grade. All right. Between that and mole maps and my other problems, we got started late. So call this mass of A on the mole map. Take 22.99 something, sum it with 35.45, whatever that is, to get to 58.44 grams of sodium chloride in 1 mole of sodium chloride. We're going to use that to take our mass of sodium chloride and turn it into moles of sodium chloride when we divide by molar mass. All right, now this is the mole ratio on the mole map, gets you over to moles B. If you pull out your calculator at this time, we'd know moles of sodium. Here's our molar mass of sodium. We find there's 5.9 grams of sodium in 15 grams of sodium chloride. We could probably solve that question that we asked at the beginning using this number and this number. We're going to do it a couple different ways. All right, now we're on to something new because I made this slide yesterday and I thought I had chapter 6 up on Moodle, but I just put my new slides up on Moodle. I apologize if they weren't up there earlier. Maybe I just missed the old file. So, inherent in a chemical formula is a mole ratio. There's 1 mole of carbon for every 4 moles of chlorine. Or I can look at that coefficient and say 1 mole of this has 4 moles of chlorine. And so that helps us do a lot of different conversions. So probably what I'm talking about a lot at the beginning of this morning is the mole ratio in that mole map to go from moles A to moles B, or moles B to moles A, back and forth. So here's a new concept for us: mass percent composition of compounds. So if I write a chemical formula and I say find the mass percent, you're going to want to be able to tell me what percent is sodium, what percent is chlorine, what percent is oxygen. The mass percent composition, or mass percent of an element, is the element's percentage of the total mass of the compound. So mass percent of some element, we'll just call X. It's going to be the mass of X in that sample of the compound divided by the mass of the whole compound multiplied by 100 to turn it into a percent. So this is exciting because it's almost like a lab where you're a chemist and you take a mass of chromium metal, you got some pure nice chromium metal, and you weigh it out and you put it in some oxygen, maybe you heat it up, and then you get a compound that you weigh, all right, and a 0.358 gram sample of chromium reacts with oxygen and you form 0.523 grams of the metal oxide. We can ask ourselves, what is the percent chromium in this compound? Now the metal oxide has both chromium and oxygen in it. We know how much that weighs, and then we know how much chromium was there, and we get a 68.4%. All right, here's where it gets ugly and you don't like me. Let's name this compound. Well, chromium's one of those metals that has different charges. The most common are chromium-2 and chromium-3. So we're going to practice finding percent composition. We already know this thing is, let me back up, 68.4%. And we did that with some experimental data. Started out with a given mass of chromium metal, allowed it to react with some oxygen, got the mass of product. And this is our definition of mass percent. Mass of chromium, per mass of the compound. That's a fraction. We like to deal with a percent times by 100. We know it's 64. So what we have to do is we're going to find the percent chromium in this, the percent chromium that, and see which one matches our data. For fun and no prizes, which one of these is chromium 2 oxide? Yeah, this one here. Some of you are drawn to the 2 and you wanna hook these up. No, what's the name of this compound? Chromium 3. 3 oxygens times -2, that's like a -6. We're gonna have to go 2 times a +3. Yeah, so this is chromium 3, this is chromium 2. So there's my chromium 2. We're gonna look up at the periodic table and see that chromium weighs something like 51.9961 plus oxygen 16.00 is close enough. So I want to take the mass of chromium and then the mass of the whole compound. So I'm going to sum 51.9961 with 16, and I'm going to divide that into 51. What's the percent oxygen in this thing? Yeah, you subtract this from 100. They got to add up. Yeah, so 23 point whatever. All right, so notice this one's going to have a little twist. I'm going to want to go 2 times 51.9961 because I got 2 chromiums. Now the mass of this whole thing, yeah, that's going to be a little more work. 2 times, and then sum that with 3 times 16. So 2 chromiums, got the mass of 2 chromiums up top. Mass of the whole thing, 2 chromiums summed with 3 oxygens. All right, so what's the name of the compound we formed in our little lab experiment? We'll just have to go back here. So our little lab experiment, we measured it with a balance and calculated that we had 68.4% chromium. Wish I could mute what I just wrote. All right, so we made some chromium 3 oxide. Chromium 3 oxide. All right, so this illustrates 2 ways we can find mass percent. We can look at a formula and calculate these things out. Let me just try not to bore you here. I'm gonna just go 3 times 16. Let's just prove something to ourselves. I need to warm up my fingers. It's been a whole week since I've played with my calculator. 3 times 16. I'm gonna just hit enter, and then I'm gonna go divide, and I'm gonna go, oh my, I gotta use parentheses. 2 times 51.9961 plus 3 times 16 in parentheses times 100%. Woohoo, there's our percent oxygen. And notice these should sum up to 100, right? All right, so when you find mass percent of a compound, it's finding the percent by mass for the elements in the compound. We might just be asked to do one element or both, and we either use, for given formulas, we use the masses off the periodic table, or we might be given some experimental data, like right here. So here with the experimental data, we just use our definitions of what percent by mass means. Got the mass of chromium, we got the mass of the whole compound, put it in there, and we see that this equaled what we just calculated for chromium 3 oxide. Any questions on that? So we found the chromium for each compound. Is there another way? So one of the next topics is an empirical formula. Empirical means experimental, and when you do that, you come up with the simplest ratio of elements in your compound. So the first step is we need to determine how much oxygen reacted. What chemical law are you going to invoke to do that? The law of conservation of mass, exactly. So experimentally, We're going to determine what these subscripts are. Get tired of using X all the time. I decided to use 2 question marks. So we know some chromium reacts with some oxygen. We form this compound. We already know what the formula is from our percent composition data. So we say this much chromium, X amount of oxygen, gives us this much chromium-3 compound. We're going to pretend we don't know it's chromium-3. We want to derive these subscripts. So we're going to use our mole and our mole map. You're going to be so glad you came to class today. All right, so I'm going to subtract 0.358 from both sides. So 0.523 minus 0.358 is going to give me that many grams of oxygen. Everybody clear on that step? Next step, determine the number of moles of each element. So now we have our 2 masses. How do we get to moles? We look up and find this chromium on the periodic table and say if I put the unit of gram per mole, I know this unit factor, and I can get grams to go away, and now I found moles of chromium. And we just found this number, 0.165 grams of oxygen. Look up and see 15.99994 on this one. We're going to just use 2 digits. Grams of oxygen, it's going to go away. And here is our moles of oxygen. So now that I've done this for a while, I look at these 2 numbers and I ask myself, is one a multiple of the other? Can I see any ratios? This one's kind of nice because it's not nice and clean and even. Sometimes one number is twice the other or 3 times the other. Sometimes I go 10 and 6.8, or maybe I go 7 and 10. I don't see any common type of multiples there. So the next thing we want to do is this thing called a pseudo formula. What does pseudo mean? What? Fake? If you notice, it sounds like I have a head cold. I took Sudafed last night. Is that fake? Fed? There's probably lots of chemical jokes built in there. Let's not. So that is, here's my moles of chromium. Here's my moles of oxygen. So I never used to use this term in this until I met Dr. Mark Main. I would just always say, set up a mole ratio. Then I'd have lots of little words to say about numerators and denominators. We're going to make this the numerator of a fraction. And it says here we divide by the smaller moles. Because most of our formulas, we have nice whole number integers. And so I look at this and I say 0.006 is smaller than 0.01. So I divide both sides by 0.006885. And you do this on your calculator. And this comes out to be 1.498. And we want to look at this and say, well, this is almost 1.5. So I think I have a 1 to 1.5 ratio. And our last step here, it says convert to whole numbers by multiplying by a small number. In this case, we're going to multiply by number 2. I was doing these slides last night, and I think the book said there's a table on page 188 of the text that gives you numbers to multiply to get rid of fractions. Well, we don't need that. Let's just think about some common fractions. Now, this one always is a pain. There we go. All right, to make this into a whole number, I'm going to multiply by 2. What am I going to multiply this by? How about 4? How about 3? So I tell students, see if this comes close to one of these fractions, and if so, multiply by the integer to get that fraction to go away. So when I multiply this thing by 2, this 1 gets multiplied by 2, so I have CR2. And what's 2 times 1.5? And actually, if I just did this, let me try it out. I actually get 2.999. 6. And we're gonna say, what's the closest whole number? And we're gonna get to 3. So we'll do more empirical formulas. We can do it by percent mass data. We can do it with just raw mass numbers from an experiment. So I told you we wanted to answer that question that we asked at the beginning of this section. So first, let's just think about sodium chloride. Had some for breakfast, put it in this stuff called Multimil. We already know this is 22.99 something. Let me get my periodic table out. Chlorine, 35.45. Does that look about right? Close enough. So if I want to find the percent sodium, there's the mass of sodium. Don't want to let you leave today without seeing this 3 or 4 times. There's the mass of sodium chloride. Let's see if we can believe this 39%. 22.99 divide parentheses. So I believe the slide. There's roughly 39 grams of sodium in 100 grams of sodium chloride. We can make that into a unit factor. So here's where I wanted to end. Maybe not so speed it up at the end. Food and Drug Administration, they're probably going to go away. Says we should only eat this much sodium. How many grams of sodium chloride can you consume and not go over 2.4 grams of sodium? So like everything, I tell you, write down a given and its units. Looking through here, most logical place to start. Here's a unit factor. Notice we probably had it the other way around up at the beginning when we got to the 39%. So we set it up in grams sodium, go away, and we're left with 6.2. Now as you're packing up, let's just do this the other way. I'm gonna go 2.4 grams of sodium. 1 mole of sodium is the same thing as that many grams of sodium. There is 1 mole of sodium per 1 mole sodium chloride. 1 mole of sodium chloride is the same thing as how many grams of sodium chloride? Should be in your notes. I just did it. 58 something. 58 what? 44?
I think, yeah, 58.4.
All right, we should get this same number. Actually, we're gonna get a little bit better number because this was actually 59.33. It'll be close, may not be exactly right on. 2.4 divide 22.99, multiplied 1, divide by 1, times by 58.44. If I'm trying to watch my sodium, I'm gonna use this rounded value. It has a rounding error in it, that's why it's a little less.